Now we turn to special kinds of power series, so-called Taylor and MacLaurin series. And before we turn to a definition, let's look at the case where we have a function that has a power series representation centered at A. For some radius of convergence, let's assume it's not 0. So we can represent the function f of x for some interval centered at A as a series from 0 to infinity of Cn x minus a to the n, where Cn are some coefficients. The first observation we can make is that when you write out what that is, it's C0 plus C1 times x minus a, C2 times x minus a squared, and so on. So except for the first term C0, you have positive powers of x minus a, which means that if you plug x equal a in the function, all the terms that contain a positive power of x minus a are 0, and what remains is just C0. So the value of the function at a is then the first coefficient C0. So in other words, if we have a power series representation centered at a, we know what the first coefficient is, C0. It has to be the value of the function at a. But now we have also seen that when you have power series centered at a with a positive radius of convergence, we can differentiate term by term and get a power series representation for f prime. And that's a series starting at 1 of Cn times n times x minus a to the n minus 1, which corresponds to differentiating the power series representing f term by term. So when you differentiate C0, you get 0. When you differentiate C1 times x minus a, you get C1. When you differentiate C2 times x minus a squared, you get 2C2 x minus a, and so on. But now we can plug x equal a in this power series and we get f prime of a, and then on the right hand side we have C1 plus a bunch of terms that contains a positive power of x minus a, which means that they are all 0 when x is a. In other words, if I plug x equal a, I get that the value of the derivative of f at a is C1. In other words, we know the second coefficient in the power series representation for f. It is necessarily f prime of a. But then I can look at this power series representation for f prime and keep playing the same game. I'm going to differentiate that, and on the open interval from a minus r to a plus r, I get a power series representation of the second derivative by differentiating term by term. So this new series is going to start with 2c2, and then the next term is 6c3 times x minus a, and so on. And again, if I plug x equal a in this, I get the second derivative of f at a is equal to 2c2 plus a bunch of terms that are 0 at a, so just 2c2. Which means that if we solve for c2, we obtain that the coefficient c2 is necessarily the second derivative of f at a divided by 2. So we already have here the first three terms in our series. And if we want more term, we can just keep playing the same game. We can differentiate term by term and get a power series representation for the third derivative, and then plug x equal a in this, and we get the value of the third derivative of f at a is 6c3. In other words, c3 is the third derivative of f at a divided by 6, which I can think of as third derivative of f at a divided by 3 factorial. And now we have the first four coefficients, c0 through c3, and with the convention that the derivative of f of order 0 is f and 0 factorial is 1, what we have is that c0, we found that it is f of a, which I can write derivative of f of order 0 evaluated at a divided by 0 factorial, because 0 factorial is 1 with our convention. C1 is the first derivative of a evaluated at a divided by 1 factorial, which is just 1. C2 is the second derivative of f at a divided by 2 factorial, which is 2. C3, third derivative of f at a divided by 3 factorial. And so it looks like the nth coefficient in the power series representation of f has to be the nth derivative of f at a divided by n factorial. And indeed this makes sense, because if you think of this power series representation of f and you differentiate n times, In particular, you're going to differentiate n times the term Cn multiplied by x minus a to the n, and what you obtain is simply n Cn x minus a to the n minus 1 the first time, then you multiply by n minus 1, so you get n minus 1 Cn x minus a to the n minus 2 the second time, and you keep going until when you differentiate it n time, you get just a constant, and you have the product of n minus 1, n minus 2 all the way down to 1. So you get n factorial Cn plus additional terms that will have a positive power of x minus a. So the first non-zero term in the nth derivative of f is going to be n factorial Cn, and then I will have terms that contain x minus a. So when you plug any x equal a in this expression, you're going to get something like that. N factorial c to the n is the nth derivative of f at a. In other words, the nth coefficient has to be the nth derivative of f at a divided by n factorial. So what we have proved here is that if you have a power series representation of the function that is centered at a, it is necessarily this series where the nth coefficient is the nth derivative of f evaluated at a divided by n factorial. And this series is called the Taylor series of f at a. So this is the only possibility for a power series representation of f centered at a. For historical reason, we give a different name when a is 0. In other words, when we have a series with coefficients times x to the n. And in this case, we call the Taylor series at 0. It's also called the MacLaurin series of f. And of course, in that case, we don't need to specify where, because when you use the terminology MacLaurin series, that means you're looking at things centered at 0. So let's look at an example of a MacLaurin series. Let's say we want to find the MacLaurin series of the natural exponential function. The derivative of order 0 is just a function, it's e to the x. The derivative of order 1, well, it's the derivative of e to the x, it's again e to the x. And you see that as you keep differentiating, you always get e to the x. So that means here we have that the nth derivative is always the same function e to the x, and therefore it's easy to calculate our coefficients for the MacLaurin series, because it's going to be the nth derivative of the function evaluated at 0 divided by n factorial. But if we plug x equals 0, we get e to the 0, which is 1. In other words, the nth coefficient for the MacLaurin series is just going to be 1 over n factorial. And that means that the MacLaurin series is the series from 0 to infinity of x to the n divided by n factorial. And this is a series that we've studied before as a power series, and we've easily established that the interval of convergence is the entire real line. So this series is convergent everywhere to some function. And if e to the x has a power series representation, it is this one. Now, it's not enough to directly conclude that there is an equality, but if e to the x has a power series representation, then we have this equality. And we'll see that this is indeed the case, but this is the question of the equality between the function and the Taylor series or MacLaurin series is something we're going to look at in the next video.